Hello everybody, welcome back to my channel here. Today we're going to take a look at a new AI paper and it's all about distilling large language models for text attributed graph learning. So in this paper what they basically do is to try to get the language information and see whether or not it can be compatible to improve graph neural networks accuracy. And and right now, I know not many people are dealing with graph processing, but hear me out because you can easily adapt this approach to give you 6% of accuracy improvement. So let's dive right into it, shall we? Now, let's take a look at the abstract here. And we're going to go through this to, together, passage by passage, as usual. So let's start. Text attributed graphs, TAGs. Okay, what do they mean by TAG? Well, TAG basically means that if you have like a bunch of nodes in a graph, right, you can represent each node with a text or a phrase, right? For example, it could be names, right? It could be Alice being a node and Jack being a node, and there would be a connection, right? And that what TAG is essentially, okay? So it's essentially connected textual documents or phrases, whatever, right? So graph models can efficiently learn these graphs, but their training relies heavily on human annotated labels, right? And there isn't enough labels, right? I mean, data sets are pretty expensive to make, and it would be nice if we have some way to solve this problem, essentially, right? And now, on the other hand, we have LLMs, large language models that have demonstrated great capabilities in few shot and zero shot graph learning, right? But they are pretty expensive. Like, I'm pretty sure you have tried to use OpenAI's API, and it's not cheap. I can tell you that. And if you're running it on your own local machine, like I am, right, it's gonna take a lot of time, right? So so in this work, what they're trying to do is to try to combine LLMs and graph neural network models and see whether or not both can deal with this issue together, right? So So the first let the LLMs teach an interpreter model, right, with its own the thinking process, right, which they call a rationale, right. And then we let the student model mimic the interpreter's reasoning without the LLM's rationale. So basically, the interpreter is kind of like a cheaper approximation, right? That tries to mimic the LLM, right? And then we have the student model trying to mimic the interpreters. So it's kind of like a snake biting another snake's tail and another snake biting another snake's tail. That's a creepy analogy, but that is what it essentially is right here. So, okay, right, let's see. Uh, right, a snake biting snake tail biting snake tail. Okay, right. This is a great analogy for me. All right. So, okay, let's see. Extensive. Okay, and then perform extensive experiments. All right. We're not gonna go into the introduction just yet. You know why? Because as usual, we need to go to the conclusion, and the conclusion is pretty important here. So, all right. So in this paper, they propose a framework to distill LMs into graph models for learning, right? So they train both predictions and rationales. I assume there would be two different loss functions here, right? They first convert the text rationales, the reasoning, the text, to multi-level graph rationales and train an interpretive model to bridge the LLM's rationale to the graph model, right? And align the interpreter based on the nature of the graph data. And based on the 4 data sets, their approach, right, improves the baseline accuracy by about 6.2%. This is pretty good, right? And let's see how they achieve it, right? So let's go back to, so let's quickly skim through the introduction, because I would surely think that you and I already know a bunch of things about this paper, right? Well, maybe not. Or maybe yes. Hold on just a second. Okay, it's about to rain outside. Anyway, text attributed graphs are graphs with text entity. Yeah, we already know that, and we don't really care about these things right now. So okay, so the current approach is to just use extract text representation with a language model, then feeding extracted text representation into a graph neural network to extract node embeddings with structural information. Thus, it allows to simultaneously capture the semantic and structural insights, right? And that boosts training progress, right? Obviously, this requires annotated labels, which is hard to get. But since we have LLMs, right, we could actually solve the data scarcity problem here. Right. So what they can essentially do, right, is to try to maybe create the labels by hand. I'm not so sure, right? But either way, right, we're going to find out what you do exactly here. Given the need for a localized model that enjoys the power of LLMs, the straightforward idea is knowledge distillation. Well, the reason why you want to do knowledge distillation is because you don't need to use the LLM for the application inferencing anymore. You just have to use the graph neural network in this case, which is much cheaper, right? So let's see right here. Okay. So right. So the question that they are trying to address is how to let language models teach graph models, right? And is it even possible in this case? Textual and graph. Is there a way to unify them? Right. So okay, blah 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 blah. Yep. And the selling point of language models is that they have reasoning, right? They can output expressive information. While graph neural networks, they only deal with the inputs and the outputs, and there isn't much knowledge being spitted out, unlike language models, right? Okay, and the second question is, right, how to transfer text rationales to graph rationales. Okay, look, this is a problem that I'm trying to solve actually, is that how do you, right, how do you like quantify, right, the text rationales and the graph rationales? If it, in my case, I would be more interested in how do you mathematically define these two things, right? So let's go for this. Okay, and the third question is how to synergize text and graph information during knowledge distillation. How do you combine them? It's like a yin and a yang. But that is a mystery that we are going to see and be solved in this paper. Text attributed graphs encompass the synergy of text and graph topology data, which is highly heterogeneous, which means it's highly different across the entire graph. How to ensure that both types of data plays out well? We don't know, right? So, okay, to tackle the three questions, they propose a framework to distill LLMs into graph models. So their approach uses the outputs of the LLMs during training via a two-stage distillation process. So firstly, right, instead of having LLMs directly teach the student graph model, they use an interpreter model that has similar structure as the student model, but can take the expressive outputs of LLMs as input. Okay, so we can imagine here it would be some kind of a tiny little model. This would be the student model, the tiny little model right here, whereas the big original model, we just call it a teacher in this case, right? And the student is an interpreter model, right? And this one is kind of like, they say it's kind of like the GNN in some way, I think. Hold on. That has a similar structure. Oh, never mind. It's the same architecture. Okay, same type. Okay, I misread, I misunderstood, whatever. Okay, so it's the same type, but one is big and one small, kind of like ResNet 50 and a smaller ResNet model. Okay, to okay, the student model is then aligned with the interpreter model that infers using raw data without rationales, enabling it to infer when LMs are not available, but LMs are not available at test time. Okay, so I think this is a pretty important part right here, is that because they know that the LLMs are pretty expensive, right, during training, so they decided to just have a smaller model that takes the place of the original LLM, which is kind of clever, you know. So essentially, you have the first stage of KD, which is that, and the second stage would be, you guessed it, from the interpreter to the GNN. Well, in my work, I'm gonna be doing this approach as well. So let's continue, shall we? To ensure the interpreter model is well trained, we convert the LLM's textual rationales into enhanced features at text level, structure level, and message level. Okay, so let's highlight that. So they're converted into three different features right here: text structure and message to inform its predictions, right? In order to align the student and the interpreter models, they propose a new TAG model, alignment method that considers the features, the discrepancies between the text and the graph embeddings. Okay, and now what they're trying to say is something like measuring the distance between the text and the graph features. Maybe it could be measuring the distance between two different feature vectors, one from the text and the other one from the graph. It's kind of hard to tell at this point, but based on my experience, this is very typical, right? It's nothing special, right? But it's correct. Okay, moving on. This approach ensures that the student model gets the knowledge from the interpreter and can perform inference without relying on the rationales from LLMs. Yep, that's the point of knowledge distillation. Okay, and now let's take a look at their contributions here. Okay, so they have a new framework for distillation, blah, blah, blah. That's already covered. Blah, blah, message level, structure level. That's not really important. LLM generated and pseudo soft labels as supervision to train the interpreter. Yep, understandable. Okay, and propose that, yeah, which we already covered. That's fine. So now now is important because right now we're gonna go straight into the methods, which is pretty cool. But yeah, obviously let us just start with the preliminaries, right? Because like not everyone is good at this field, so let's get into it, shall we? Okay, learning on text attributed graphs. So graph learning aims to learn the representation of graphs obviously, right? Representation learning. Most existing work on graph learning follows the paradigm of pre-training a language model, trying to encode the text features into embeddings, right? So from the text into vectors, and then using the GNN to get those to get those embeddings, and trying to create the node embedding, right? So it's a two-step process essentially. So this approach, okay, uses both LLM and GNN, and here's a whole bunch of mathematics, but essentially this is the most important part right here. Essentially, you got the text features and you put it into the LLM and you get some kind of a embedding from the LLM, right? And the LLM is they use a BERT model for that. If you know what the BERT model is, it's essentially imagine GPT, but it doesn't generate tokens, right? Well, that might be a bad way to put it, but it essentially is the encoder of the original transformer. Well, if you're interested in learning that, I would say there's plenty of other videos about this. But yeah, let's continue anyway. After getting the text embeddings as initial node embeddings, okay, a GNN uses message passing to learn structure-aware embeddings for each node. Okay, if you don't know what a message passing operation is, right? Imagine you in your neighborhood, right? Maybe that's not a good idea, a good example. Okay, imagine you have like your friends around you, right? And you guys are talking to one and another. Well, message passing is basically just that, just a few notes, right? Sharing information between one and another, right? That's all, right? But obviously, right, that can be described using a mathematical equation, but I'm not gonna go through that for now. But what you really need to know is that after performing that, you will get some kind of an embedding for each graph node, and that's really it. So H and K represents the embedding of node in some k layer of the GNN of the graph neural network. All right, and that's that. Okay, and finally, right, node classification is made with the final node representation by feeding in the embeddings, the node embedding into a multi-layer perceptron to generate T hat n, right, where L is the number of message passing layers and T hat n is the predicted soft labels logics. So it's predicting the class, the identity of the node. Okay, and now let's get into the meat of the paper here. So methods. Okay, to distill LM into a local model. Okay, so they are doing the first step, right? Trying to distill it into an interpreter, right? Okay, so for a graph and LM, the goal is to train a student model, which is basically LMS, and a GNNS, a small graph neural network, right? During the learning process, no ground truth labels are provided, right? And only a subset of nodes retrain and their textual features are allowed to be exposed to the LMs. Okay, let's highlight this part right here. Okay, let's see. So there are no ground truth labels provided, and you only get a subset of nodes and the textual features, and we show it to the LLMs. Okay, so it's essentially imagine the entire graph, but you mask out half of it. I think that's what it means. I don't know, but let's find out. Okay, so and to say that this is a unique challenge, these are great challenges. You know, difficulty in leveraging LMs to teach graph models, and then talk about how hard it is to do so. Okay, so for instance, LMs generate text information, whereas the output of the graph models are just class labels. True, right? Because you one have text and the other one is just some like class label, right? It doesn't even make sense. How do you even like join them together? It's kind of hard, right? So traditionally, what they would do is they try to align the logics and the parameters, right? But this is not very effective. They say it's not an effective approach. Well, I'm just gonna assume that's true. Okay, next, difficulty in transferring text rationales to graph rationales. Yeah, this is what I'm talking about here. Yeah. LLMs can provide text rationales, which the graph models cannot naturally understand. Yeah, true. Transferring the text rationale is problematic, essentially. Okay, look, I'm more interested in this problem right here because I'm currently facing the same thing, right? Anyway, next. Difficulty in synergizing text and graph information in model distillation. So they talk about like it's hard to align them together, right? But it's also quite hard to preserve the text and graph information at the same time. Yeah, yeah, that's all relevant. I feel it in my heart, you know. But anyway, okay, let's get into it. Okay, so to solve that, they propose a framework that bridges these two types of models. So, and they gap a lot of things, right? LLMs can provide rich knowledge on graph learning rationales. Just let me have a sip of water here. Ah, fresh. Okay, let's go. Okay, so a naive approach, right, would be to use LLM provider rich knowledge as additional features. Makes sense in figure 2, however, right, such as in figure 2, however, although the rationales can help, using them as inputs usually leads to worse test performance due to the distribution shift of features at test time. Uh, Look, I highly doubt that. I mean, if you are still using the LM even during test time, it should perform. Look, if it works for the training part, right, it should work for the test part because you're still using the LLM. It's not like you completely dismantle it after training, right? I mean, I'm not an expert, right? But that's just my opinion here, and I could be wrong, which a lot of people are. Anyway, an alternative solution is to only use knowledge, okay, such as the LM's predictions as supervisions to train the model so that the training and test features can be in the same distribution. Well, however, right, however, you might as well not use an LLM at that point. Because the selling point of the LM is that it has this rationale, it has this thought process thinking, right? Wait, hold on, just give me a second. Just give me a second, one moment. Don't go away just yet. Wait, just give me 1 second, please. Just stay with me here. Don't skip, okay? All right, I'm back. Sorry about that. Let's continue. So, okay, right. All these are really great problems, right? But I want to see the solution already. right? So to address this problem and ensure the model can generalize to original features without rationales at test time. Well, I mean, if you use the rationales during at test time, it's no problem, right? Anyway, right? We propose a solution that is first to use the rationale to train an intermediate model, and then use the intermediate model to train the student model with the same architectures, but takes the raw features without rationales. Okay, fine. Okay, so let's go into this figure now. Okay, let's see if we can understand this without reading the other text. Okay, so first thing you see here, right? Oh my God, spelling mistakes. Oh my goodness, it's so jarring. It's like the same spelling mistake for some reason. Okay, right. So starting off with an LLM, right? And then produce some kind of a text embedding, right? They call it text encoding, whatever. And then presumably you feed it into a student model, a GNN student model. Is it? I think so. It's called. Wait, hold on. No, 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 no. Wait a minute. Okay, right. I see it now. So there's two branches that you got to do the same thing. So this is the GNN part, right? So this is the graph neural network part, and this one is the LMS part, right? Sorry, LLMS part, and this is the GNNS part, right? So you basically train the interpretive model at the same time you train student model. No, 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 no. It can't be right here. Okay. You know what? This figure is not that clear, honestly. Ah, man, this is not going well for me. Um, how about this one right here? Okay, we have a graph, and somehow it gets into the LM, and there's like a connection to the interpretive model, and there's like a bi-directional connection between the student model and the interpretive model. I guess that's knowledge distillation, KDE. Maybe this is KDE in some sense, and yeah, it's not that clear. It's not that clear. Okay, maybe the figure captions can help out a bit. Illustration of our LM to graph KD. Okay, general distillation framework. We propose to distill the knowledge of an LM by leveraging LM generated rationale and supervision to train an interpretive model and then align the student model on raw features without the interpretive model. Okay. Part B, the training of the interpretive model with rationales and pseudo supervision. Okay. So the interpretive model takes rationales as input, such as keywords, key edges, and key messages. All right. LM generated pseudo supervision, including pseudo label and soft labels, is used to train the interpreter model. The proposed model alignment framework, part C. All right, here. The student model, which takes original features as input, is aligned. Okay, so the student model is aligned with the interpreter model on text and graph levels based on the discrepancy between raw inputs and rationale enhanced inputs. Okay, look, there's a lot of stuff going on here, and it doesn't even cover things like probabilities, alignment, and all those things in the figure caption. So I tell you what, sorry. All right. So wait, hold on. Okay, let's see what else do we have in here. Okay, okay, it's quite okay. There's 3 pages. Okay, let's do this. All right, involves an immediate intermediate interpretive model that bridges the LM and the student model specifically to extract the knowledge of LMs on the graph learnings. We let the LMs produce rationales to enhance the features and provide supervision green error to train the LM. Sorry. Since the interpreter model and the student model share a similar model structure, the student model, the student model can be aligned with the interpreter model by aligning their latent embeddings. Hold on. Okay, wait a minute. All right, they're saying something important here. Since the interpreter model and the student model share similar model structure. Wait a minute, there's a contradiction here. I thought at the beginning you say that they share the same structure. I mean, the big language model shares the same structure as a small language model. Isn't that what you're saying here? Wait. Wait, hold on a second here. Hold on a second here. Are you gaslighting me? Okay, just give me a second here. Similar. I'm trying to find out. Wait a minute. Okay. Uh. Oh. Okay. All right. It's my bad. My bad. I thought they wrote something like the teacher model is about the same as the student model. So, okay, right. My bad. My mistake. Yeah, I take ownership of my mistake. I'm sorry. Okay, moving on. All right, but I guess the important part right here is that for effective knowledge distillation, the architecture between of the student must be the same or similar. Okay, I guess that's something that we learned right now is that it must be kind of similar in order to learn effectively, maybe, or maybe not. It's hard to tell. Several specific questions arise that needs to be addressed, and I guess those questions we already know what those are. So let's get right into 4.3. Interpreter model, zero shot graph learning with rationales. Okay, let's go. To tackle the problem in transferring text rationales to graph rationales. Okay, now this is what I need to know. This right here, okay, let me just give it like a big star right here. Big star. All right, let's do this. Into multiple level enhanced features, right? The goal is to train a strong interpretive model consisting of a language model teacher and GNN teacher. Okay, the rationales behind a graph model decision can be depicted as a prediction is primarily made based on which parts of the text on which neighbor nodes. Okay, wait a minute. That means on which part? Okay, so basically what it says is that the node, the prediction on of the node stuff is based on its local neighborhood. That's what it essentially is. Okay, since the graph models cannot directly take the textual the rationales to breach the style of textual graph rationales, we convert the text rationale into three forms. One is keywords in text, key links around central node, and key semantic messages from neighborhoods. All right, so essentially from the text, you just extract out different stuff, and then hopefully you can construct a graph out of this extracted stuff. At least that's what I think it is, right? And if we take a look at this graph right here, yeah, you have different texts, right, that are extracted from the original text, and you try to like construct a graph for those texts. Yeah. So, and essentially, you have like two of the same type of data, right? Graph and graph. It is compatible. Compatible as vanilla and chocolate, I think. We leverage LLMs to generate supervision to train the interpreter model, including pseudo soft labels and pseudo labels. Okay, and I illustrated their training in the figure above. Okay, we prompt such prediction and reasoning in 3 steps. We input the text attributes of each node along with those of its neighbors. Right, so you get the text attribute of the main node along with its local neighbor, right, into the LLMs to generate some kind of a pseudo label or soft label. Okay, actually, speaking of which, right, in this case, what would be the pseudo label? So let's take a look, shall we? Let's go into internet and find out. So what do they mean by pseudo label, right? Or maybe even ChatGPT might have a proper definition for it. So let's go into here and let's find out pseudo label. What's that? And it's going to say something. Pseudo label is a method by leveraging the small amount of data, labeled data, because you have a ton of unlabeled data. All right. All right. So the train model is used to predict the labels for the unlabeled data. Okay, right. I see. So you train it on the small set of labeled data, and you use that model to predict the labels for other data. So sometimes only the pseudo labels with the highest confidence are kept. In other cases, all pseudo labels might be used. All right. Retrain the model. Okay, the model is retrain both the original label data as well as the pseudo label data, and it could improve it. It could, right? But I don't think it's a guarantee approach. So how about soft label? What is it really? What is soft label? Okay, soft label is essentially the logits, right? Essentially the probability distribution of whether it's a cat or a dog. The AI model might be thinking that, oh yeah, that picture could be 60% dog, but it's 40% cat, you know, unless you have a cat dog, in which case it would be 50-50. That is the pseudo label. You see, hard label is like 0 and 1, whereas soft label is some kind of a smooth distribution, right? Well, not exactly smooth, but you know what I'm saying here. Anyway, we then supply the nodes text and its pseudo label to the LLMs to identify critical keywords within the node's attributes for classification. Then we feed the text of the node and its neighbors along with its pseudo label into the LLMs to identify essential links and messages for the classification. Okay, and I talk a lot about these pseudo labels and how to generate them, how to generate those soft labels, right? So essentially what they have here is this. So ln and yn is produced by using the LLM and applying it on what's x in this case. Let's see, did we talk about x? Okay, so variables x. Okay, this means that calling LLM with prompt L and variables x n. Right. So in this case, you have the prompt and you have some kind of a input variable xn along with xi, right? Okay, so the input is something like this. Input, we want to classify a paper into three different categories. Into these categories, neural networks, genetic algorithms. Please identify logics like probabilities for each class and give your final classification. The paper is blah 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 and its neighbors are blah blah blah. And then the LM would give you a probability distribution, right? And you can select the highest probability class, right? In this case, it would be generic L. No. Another spelling mistake. Another one? Oh, come on. Proofread your paper, my friend. Genetic. Genetic algorithm. For goodness sake. Anyway, that's a small issue right there. Okay, keyword recognition. LLMs have been proven to have the capability to extract those keywords. Okay, right. So, okay, extract the keywords using another different prompt. Where's the prompt? It's KW, right? Okay, the blah blah blah. Okay, please identify at most 5 words in the provided text. Yeah. So essentially, right, it's actually quite simple. You just say, right, you just prompt it, right? Okay, and the next one is please identify a subset of important neighbors and at most 5 keywords of each important neighbor that would help most to classify the central node into the category of neural networks. And then you say this paper is blah 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 title, and you can describe all the neighbors, and it would give you this thing right here, this response, right, which you can use as a prompt. So, okay, we're going to skip some of the details because I don't think it's that necessary. But what I do think is necessary is this one right here. So this is the, okay, so, all right, let's see. So this is, I think this is the loss function, right? It has to be, right? So, okay, L label is cross entropy loss between the T and the Y, and L logits is the mean square error between the T and the L. And then you take sum of them to get your LT term. All right. Okay, this is getting tiring. Okay, to achieve better LLM-free prediction at test time, they propose a new alignment method for the graph. And the new alignment method is essentially trying to get the textual and the structural embeddings LM and GNN information between the interpreter and the student models. Right. So we want the student model to give more similar predictions to the interpreter model, but does not need to take the rationales of the as input. Okay. So I think they are defining two different metrics in this case. One is semantics alignment and the other one is structural alignment. Okay, and there are two different equations, right? One for the semantic and one for structural. Okay, so if we just like rush through this two equations, right? Essentially, what I think it is that okay, you have some kind of a similarity function, right, between xn and xnt, right? Oh man, my voice. Okay, and now you have some kind of a distance metric between the student and the teacher embeddings, right? So as you can see right here, I think this is a very important part, the distance between their two different text embeddings, and we are trying to keep them to be more aligned, to be more similar. That's why we need to minimize that. Okay, The next, structure alignment, right? So they also want to focus on the nodes with more discrepancy between the original and the rationale, enhanced structure. Therefore, it's almost about the same thing, but it's really just applied on different stuff, essentially, right? Okay, so you have the distance, and you're trying to minimize the distance between the node embeddings. Pretty simple, right? Okay, now let's move on to the training objective of model alignment. Okay, so you think those two loss functions are enough? Well, it's never enough, right? Which is why we have a new loss function here, right? A new loss function, one for the label, one for the logics, one for the semantic, and one for the structural. So yeah, this group is for standard normal knowledge distillation, and the other one is for graph model alignment, right? And obviously they have these lambda parameters, hyperparameters, which you can try to adjust and to get the best test, not really test, but the best validation prediction accuracy, right? So obviously not too high, not too low, just in the middle, just right, and that would be it. So, and then obviously, you got a new approach, you have to test them out, and this is what they did right here. So they tested it out on the Quora, PubMed, and OGBN products and archive 2023, right? So those are different types of graph data sets. But what we're interested here is actually this part right here. So this is their approach, right? LLM as the teacher. So obviously, look at the score right here. Look at that. Look, I don't even need to say anything. Just look. Just look. It's 80+%, right? In comparison to other methods, those are like 60 plus, and that's it, right? So this is a pretty good approach. It's pretty good, right? Even if you take the standard deviation into account, it is still very high. Like, I'm not gonna complain about that. Great job, authors. Great job. Is it really 6% improvement though? I think it's a bit more. Maybe not, I guess. I don't know. Best performance on all data sets. Okay, let's see what they have here. So okay, so in this case, they are trying to see what's the effect if we increase the training data more and more and more, right? So they found out that, this, wait a second, wait, you say percentage, right? Does this mean 0.6%? I don't know, but I would think that it's 60%. It has to be 60%, right? I mean, whatever. Either way, their proposed method seems to reach great accuracy, right, for Quora, but for something like OGBN products, it's approaching about the same. But as you can see, there's always this like gap in between different approaches, right? And their approach seems to be very high in accuracy, which is just wonderful, right? So this is a good paper. I mean, yeah, it's a simple, good approach, and it works. And that's what we want essentially. And let's take a look at this one right here, right? So and And they show that, okay, if you don't pre-train, the accuracy is going to be quite bad. I mean, not quite bad, but it's relatively bad. But if you add in some pre-training, your accuracy becomes higher by quite some margin. And also the prediction accuracy standard deviation shrunks apparently, and it's the same case for other different models. So, and then obviously there's a compare their approach in terms of test time. So the test time are about the same, but the training time is better than Giant, which is an annotator role, right? But obviously it's higher than these two above. I mean, I'm not gonna complain, especially when it achieves this much of accuracy improvements. Well, obviously, one thing is for sure that is the number of tokens are different. I don't know what that would contribute towards, but it is what it is. Okay, so all right, and we have the hyperparameter search. Like I say, right, you need to have like a balanced lambda function, right? As you can see, it always starts off with the lowest and it goes up and it goes down, and you got to find the in between point, just like that. It's always at the middle. Well, technically, this is not in at the middle, but it's somewhere close. Either way, right? It's pretty good. All right, and this one is the ablation study, and it shows you the accuracy of when you remove some components out from their approach, right? How well would it work anyway? As you can see, right? If you starting off with the baseline, right? And if you compare it with the proposed approach, um, this is actually kind of interesting in one way, right? Is that it's really model specific. As you can already tell, yes, they did try to remove all the components piece by piece, but as you can already tell, right, some components are much better just to be left out, and it results in better accuracy than having the entire thing together, right? I don't know if they explain it, but it's not really that important right now. But if you want to know why this paper, you should probably go and read this paper in more in depth. But either way, it's pretty good, right? So, all right. Okay. So, oh dear. Oh dear. So, I guess that's it for this video. So if you like what you saw, oh dear, and it's 53 minutes already. Right. Yeah. So if you like what you saw, right, or you're wanting to discuss any other papers, just let me know down in the comments below, and make sure to like, comment, and subscribe, and I will see y'all in the next one. Bye.